Okay, everybody. We're going to start by just looking at this desmos.com. And what I'm going to do is I'm going to create a point, AB, and I can move it around. And let's imagine that there's a vector going from 0, 0 out to this point. So we're thinking of the point as a vector pointing from 0, 0 to here. Okay? And then what I want to do is I want to put AX plus BY. So right now A is 2.98, B is 1.5. And I'm doing AX plus BY equals C. And I'm going to set C at 0. Now, what this gives is a line. And as I move the vector at the point A comma B, the line changes its tilt. If I move the vector sort of in the same direction but out, and now it's a really long vector, all going from 0, 0 all the way out here, the line is the same as if I keep that same direction roughly and make it a very short vector. So the length of this vector doesn't matter, only its direction for determining the tilt of a line. Now, AX plus BY equals C is over here, but this has been C equals 0, and so you see that the point 0, 0 is on the line. But now if I take C and I make it to be positive, watch the line. Okay, so now the line moves towards the tip of the vector. If I make C negative, it moves away. So this is, we'd call it the constant term. This determines how to shift the line off the origin. Now let's go to 3D. Here I've got a similar thing. I've got some sort of vector that I'm calling n for normal. And this time, well, it's very similar, except instead of a line, it's the tilt of a plane. And what is that plane? Well, that plane has, well, if this point n is the point A comma B comma C, now C is not the constant term, but it's now AX plus BY equals CZ. AX plus BY plus CZ equals D. So now D is 0. If I make D positive, it will... Oh, come on. Is it not working? Well, that's... Oh, there we go. So it'll shift that plane off the origin. It'll shift it in the direction of n. Now, as D becomes negative, eventually it'll become negative, it'll just shift the other way. And so this is what we're going to see in equations now. Okay, so let me go back to the iPad. Okay, so first question, what are orthogonal vectors? What are orthogonal vectors? So first, there's other words for this: normal, 90 degrees, pi over 2 angle, perpendicular, right angle, orthogonal. These are all the same word. And now, so orthogonal has to do with dot product. And remember, here we have sort of a summary of dot product. The main thing is that the dot product of V and W, its definition is that it's the first components multiplied plus the second components multiplied plus the third components multiplied. If we have V1, V2, V3 are the three components of V, and W is similar. So that's its definition. But then we learned that that's how we calculate it, but we can interpret it as it's the length of V times the length of W times the cosine of the angle between them. Now, the cosine of pi over 2, the cosine of 90 degrees is 0. So whenever the angle is a right angle, then this becomes a 0, and the whole thing is 0. And so whenever the dot product of two vectors is 0, that means that the angle must be right angle, 90 degree, pi over 2, normal, orthogonal. And so that's sort of the main observation here. So let's look at these vectors in our example. This one is 1, 2. This one looks like it's 4, minus 2. And so their dot product is 1 times 4 plus 2 times minus 2. And that's 4 plus minus 4, 0. And sure enough, you can sort of see the angle between them is a normal angle, an orthogonal angle, a 90-degree angle. Okay, and let's look at these ones. So these are in 3D. This one looks like maybe 2, 0, 0. And this W here, oh, that's wrong. So this V looks, usually this is, okay, so we have to name these axes. Let's call this the first axis, second axis, third axis. Or we could give coordinates like this is the y1 coordinate, y2 coordinate, y3 coordinate. Or we could call it x1, x2, x3. But usually we have first, second, third. So then V would be 0, none in this direction, comma, maybe 2, 1, 2 in that direction, comma, 0, none in this third direction. Okay, but that's sort of up to us, our choice. Let me sort of get this out of the way. And W maybe then, well, it's only in the first direction, nothing in the second, and nothing in the third. So maybe its components are 5, 0, 0. Let's take their dot product. 5 times 0 plus 0 times 2 plus 0 times 0 is 0 plus 0 plus 0 equals 0. So the dot product of V and W is 0, which makes sense because they're at 90 degrees with respect to each other. And so, these axes are called orthogonal axes because they're all at 90 degrees with respect to each other. Okay, so that's the second example. So what are orthogonal vectors? Answer. Vectors such that, so vectors maybe V and W such that the dot product is 0. That's it. Any dimension, this is what it means to be orthogonal. Okay, and from this formula up here, the cosine is has to be 0, so the angle is pi over 2, or negative pi over 2, or 90 degrees, or negative 90 degrees. Yeah. Okay, next question. What are all vectors orthogonal to a fixed vector V? Okay, so let's look at this vector 3, 2. And I claim that 2, negative 3, 2, negative 3 is orthogonal. Let's check that. 2 times 3 is 6, plus negative 3 times 2 is negative 6. Sure enough, the dot product is 0. But, that's not the only one. What about the vector U, V, W? How about U is 4 times negative 6? And again, the dot product V dot, we can write the dot product many ways, is 4 times 3 plus negative 6 times 2. That's 12, and minus 12, that is 0. And so again, this is 0. And in fact, when we're finding all vectors orthogonal, we just take any vector on this line. That vector, that vector, that vector, that vector. And this entire line, in fact, extending forever in both directions, is the set of vectors that are orthogonal to V. So we could even say, this is the set of all the x in R2 such that V dot x equals 0. And another way to write that is this is all the x1, x2 such that v1 x1 plus v2 x2 equals 0. That's just the definition of the dot product. This is a shorthand symbol, and this is what it really is. Okay, I'll close my set. So the set of all these points, the set of all these vectors, is this line. Okay. Same thing in three-dimensional space, in any dimension. The set of vectors orthogonal to a fixed vector v, well, in this case it would be the set of x in R3 such that x1 times 2 plus x2 times 4 plus x3 times 3. By the way, I could have written like dot 3, but typically you would see it like this. We put numbers before the variables, although it doesn't matter. Equals 0. This is the dot product equals 0. I mean, we could have written this as, because we gave this vector a name as v, we could have said that this is all the v dot x equals 0. We could also put it that way. It's the same symmetric sort of thing. And yeah, so that here's the set. This is the description as all the things that the dot product 0. Now what is it? Visually, it is the plane orthogonal to that vector, just like we saw in GeoGebra 3D. And so this plane goes through the origin, just like our line went through the origin. Why? Because the vector 0, 0 is orthogonal to everything, right? 3 times 0 is 0, plus 0 times 2 is 0. So 0, 0 dot v is 0 for sure, which is 0, 0 dot, v was 3, 2 dot 3, 2 is in fact 0. And that'll work over here too. That's why the origin is in this plane. Okay. That's it. What are all the vectors orthogonal to a fixed vector? It depends on the dimension, but in 2 dimension, it's a line at a 90-degree angle with respect to that vector v. In 3 dimensions, it's a plane at a 90-degree angle with respect to that vector v. Okay, so what are equations for lines and planes? Lines in 2 dimensions, well, lines in R2 can always be, lines in R2 have equations like ax plus by equals c. And so if we wanted, this is the most general equation. So any line in the plane has an equation like this. And thinking about that, we could say that it's, lines in R2 have equations like n dot x equals c, where n is some vector, in this case maybe it's a, b, and x is x comma y, so this is sort of silly notation, but and c is a real number. Okay, so you could also just say if n is the vector n1, n2, if x is x1, x2, these are our variables, and c is in R, then we get the equation n dot x equals c, which really means n1 x1 plus n2 x2 equals c. So those are equations for lines. What about planes? So a plane in R3 has equation, it's not working right there, equations like n1 x1 plus n2 x2 plus n3 x3 equals c, where x is variable and n is a fixed vector, called the normal vector. C is a real number and gives the shift of the origin. Okay, so, and because of the dot product, we can say that, you know, every plane in R3 is n dot x equals c for some n in R3 and c in R. And really, what I should say here is that every plane, the plane is the set of x's in R3, such that, so this is a set, the set of all x's such that n dot x equals c, where n is some vector and c is a real number. And I want to point out that there are actually, you know, for a given plane, there are many normal vectors and scalars c, normal vectors n and scalars c that describe it. Why is that? Well, because if we have some line, let's say even just a line through the origin, then if this is n, that would work, but also this n would work. So sort of even this n over here, pointing that direction, would work to say n dot x equals 0. Any of these three choices of n would work. So you have a lot of choices of n. Now, if we took something and shifted it off the origin, so let's take like this line. Now, you know, this sort of an n would work. I usually draw it somewhere on the line. Like I could draw it here. It doesn't matter where I draw it. In fact, I could draw it based at the origin, as long as it has a 90-degree angle to the line. And, you know, if I chose this n, then there is a specific c that will make it work. And in the next video, we'll discover how to find that vector c. But this is all I wanted to say for now. What are equations for lines and planes? They look like this, which can be written as a dot product. And they look like this, which can be written as a dot product, because this is a dot product. So that's all for now. What are all polynomials in n equals 1, 2, 3 variables of degree d equals 0, 1, 2, or 3? What are all possible polynomials in one variable? What are all possible polynomials in 2 variables? What are all possible polynomials in 3 variables? And for each of those, what are they in degree 0 and degree 1, 2, and 3? So because we just saw these are going to be called linear, I just want to show you what else you can do, and this I find helpful. So let's take one variable. If we just have one variable, let's call it x, then we could have x to the 0, we could have x to the 1, we could have x squared, we could have x to the 3rd, we could have x to the 4th, etc. Now x to the 0 is just 1, x to the 1 is just x squared, x to the 3rd, and so that's it. And so this we'd say are constant, the constant term. This we'd say is linear. This we'd say is quadratic, and this is cubic. But the other way to say it is these are degrees: degree 0, 1, 2, 3. How about 2 variables? Let's call them x and y. So again, we just have one constant, but then now we have 2 things. We could do x or we could do y. I'm not going to put commas, I'm just going to separate them. So this is I'm not trying to write x times y right now. That will be later. In fact, it'll be in degree 2. I have x squared. Now I could have x times y. And then I could have y squared. Now in degree 3, I could have x to the third. I could have x squared y. I could have xy squared. And I could have y to the third. And it would keep going in degree 4, and etc. So cubics, there's 4 different kinds now instead of just 1. Quadratics, there's 3 different kinds instead of just 1. Linear, there's only 2 instead of just 1. But constants, there's always just 1. And that'll work also when we go to, let's choose pink. If I have x, y, and z, 3 variables, then again I just have the constants. Now I have x, I have y, and I have z. But now I have x squared, I have xy, I have xz, and I have, what else? Y squared, I have yz, I have z squared. Wow, there's 6 different things in degree 2 now. Degree 3, x to the third, x squared y, x squared z. Now let's do the linear in x, but now quadratic in y squared. X, y, z, okay, that's still degree 3. X, z squared, degree 3. And now we have a y to the third, that's degree 3. We have y squared z. We have y, z squared, and we have z to the third. So there are 5, 10 different degree 3. So let's just look at that for a moment. So, and we could keep going there too. It's going to get a lot. There's going to be lots of. And this is how you build any polynomial. So remember, like, the linear polynomials, these give us flat things, like lines and planes. That's why a line is given by like something x plus by equals a constant. So this is like c times 1 is here. And that's it. That's all we can do because there aren't any more. If we wanted to do something more complicated, we would have to go up a degree, and then our object would not be a line. It would be something that's curvy. Same thing. I just want to get rid of all these pink. Same thing in oops. Here, this is all we have. So like the only thing we can do is ax plus by plus cz, which, then our normal vector would be a, b, c. And then we can put a shift, so then our constant term would be like d times 1 to shift it off the origin. And that's it. That's all we can do with 3 dimensions. So that's why when we're doing flat objects like lines and planes, we can only use these linear terms. If we start using higher order, we start getting curvy, interesting things. And those are harder. So, and that area of math would be called algebraic geometry. It studies what happens to the geometric objects that are described by higher degree polynomials. One thing that I'd like to point out here is that what's always useful to do is to look at Pascal's triangle. So I always do 1, 1, 1. And then I can build it as 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. I could just keep going. This is kind of fun to do. And it's really useful because this will come up in many places. For example, look at the degree 1 polynomials. There's always 1. There's always 1s. Now, when 2 variables, you have 1, 2, 3, 4. And that's this. 1, 2, 3, 4, etc. And then in 3 variables, we have 1, 3, 6, 10. 1, 3, 6, 10. So anyway, this is sort of interesting to me. And I just wanted to take a moment to just say, like, if you're just going to use polynomials, this is all you can do. And so that's why the linear equations are just the simplest. Okay.